Hello, students. I'm holding a thermal detonator. No, actually, it's just a simple device called a calorimeter, and I'm going to show you how to use it today in the pre-lab video for heat capacity. So suppose we have a sample of a pure material. Here I have aluminum, and it's at room temperature, and we place it next to some other material, gas, liquid, or solid, and the other material is at a higher temperature than room temperature. Maybe we place it over a flame. A type of energy we call heat energy will spontaneously flow from the hot region to the cooler region, which in this case is the sample. And we say energy is conserved, so that heat energy goes into increasing the internal energy of the sample. Well, what is the internal energy? You know, it's the jiggling around of the atoms in the solid. We can think of them as little mass spring systems, kind of like in the periodic motion lab. So the increasing internal energy increases the amplitude and frequency of vibration. Now here in the macroscopic world, we detect that as temperature. So the increase in internal energy increases the temperature of the sample. Now it's an interesting fact that at room temperature, usually, this input of heat energy is directly proportional to the change in temperature of the substance. So we need a constant of proportionality, and that is the heat capacity, or for us, the specific heat. And this constant at room temperature and pressure will be a particular value in all cases for aluminum. But suppose we have another pure sample, say copper, and suppose they were of equal mass, my copper and my aluminum sample, and we were to put, say, 5 joules of heat energy into each, we would find the change in temperature would be different in either case because the constant of proportionality would be different. So copper has a different specific heat than, say, does aluminum. So some materials we say have higher heat capacity than others. So we have a little setup today that will allow us to experimentally measure the specific heat for a pure sample. So suppose we were going to use aluminum here. So the first thing you would do is you would bring the aluminum up to a high temperature by placing it in boiling water. That's usually what we do. So we have water over here on a hot plate. It's not hot at the moment. If it is, be sure to use tongs here. And we have a thermometer there we can use to measure the temperature. So let me tell you a little bit about the calorimeter here. So there's an outer cup and there's an inner cup that comes out like that, and it's insulated on the inside like that. You can see it there. And the idea is you would put a known mass of water in here. It will be at room temperature. And then there's an insulated lid and a thermometer that measures the temperature of what's going on in here. So we have water here at room temperature. We'll heat up the aluminum to boiling temperature, probably about 100 degrees C. And then you'll quickly place it in the cooler water in the calorimeter. So spontaneously, heat energy will flow from the hot sample into the cool water, and you'll kind of stir and monitor the change as time goes by. So the temperature will increase on the thermometer here, and it will reach a maximum eventually, and you want to record that maximum temperature. So given the initial temperature of the warm sample, the initial and final temperature of your calorimeter, we can use energy conservation to determine the specific heat of the unknown sample. We will, from a table, get the specific heat for water, and you'll see the equations to do this in the write-up for this particular lab in your manual. So if you're very careful, you'll get a very good estimate for the specific heat of the material. So one weakness in the experiment is, of course, some heat energy is lost from the inner cup. You'll also have to account for the energy that is lost to the inner cup itself. It is aluminum, and you'll record the mass. You'll find the mass of the inner cup, and we'll assume some of the energy was lost to the energy cup, the inner part of the cup, and that helps the results a little bit. That makes it a little more precise, but we still ignore the fact that we lose some of the energy from the inner cup altogether. So it's Never perfect, but you can get very close if you're very careful in this experiment. So using the calorimeter, pure samples to determine specific heat. We'll have some boiling water in this lab. You'll want to be careful and use the tongs. And so if you're careful, you'll get very good results in this lab for specific heat. So I look forward to seeing you in the lab.